For our project, we'll be discussing the use of algebraic manipulation and trigonometry in mining draglines. Draglines are heavy pieces of equipment commonly found in open-cut coal mines where they are used to remove overburden and undercover coal that can be mined. Draglines are amongst the largest mobile land machines ever to be built. Draglines undergo extremely large forces when in operation, due to the fact they are very large pieces of equipment and can move up to 450 tons of material in a single cycle. The number one priority in a mine is to make as much money as possible in as little time. As such, it is vital for the engineers in the mining sector to calculate factors that will affect the performance of the dragline and hence ensure that the dragline is operating at its best potential to make more money. A major factor of a dragline that needs to be considered is the calculation of reach factor. An economically efficient mine design relies heavily on engineers calculating the reach factor of the dragline to ensure that the mine is able to accommodate such a large piece of machinery. As such, the group will take you through the use of trigonometry and algebraic manipulation in calculating the reach factor of a dragline. Other parameters such as the operating radius can also be found from the following equations. Here is a diagram of the typical operating process of a dragline, where we can see that the dragline is sitting on top of a high wall and next to it is the spoil pile. Next, we are given all the design parameters that are involved in a dragline. From these design parameters, the following lines of working were produced to derive the reach factor formula. Firstly, the area of cut slice is given by A equals WD, and the area of the spoil pile is A equals WD outside of 1 plus S. Through the use of trigonometry, we can also express the area of the spoil pile as A equals WT plus WH minus W on 4 times tan theta, and which provides us with the equation WD outside of 1 plus S equals WT plus WH minus W on 4 times tan theta. As such, by equating lines 1 and 2, we can derive that H equals D outside of 1 plus S plus W on 4 times tan theta close bracket minus T. From the prior diagram, it is clear that the reach factor is equal to the sum of the horizontal projections of high wall slope and spoil pile slope. Therefore, RF equals D cot beta plus H plus T times cot theta, and equating for H gives H equals RF minus bracket D cot beta close bracket over cot theta minus T. However, as spoil pile height is not always known, we can eliminate it by equating lines 3 and 4, which produces the top line. And as such, by equating for RF, we produce that D outside of 1 plus S over tan theta plus W on 4 plus D on tan beta is equal to the reach factor. Therefore, for a real-life example where the reach factor needs to be calculated, we are given the following parameters. The overburden depth equals 20 meters, swell factor equals 0.3, spoil pile slope equals 30 degrees, pit width equals 40 meters, and the high wall slope equals to 45 degrees. By subbing all this information into equation 6, we find that the reach factor of the dragline is equal to 75 meters.